Good morning, friends and dear students. I feel immense pleasure to be here again for my course Flight Mechanics. This course belongs to the fourth semester of Aeronautical students from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. Today my topic is problem solution of cruise and climb flight. I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. Today my topics are problems for maximum endurance condition, larger ground run, limits of load factor, finding the wing loading, and finding the stall speed. So these are the 5 problems which I am going to solve in the next slides. Just I will discuss something about Man Ki Baat. Here in flight mechanics, I am mainly focusing on the aircraft performance. Once I talk about the aircraft performance, it relates to the phases of the flight. Phases of the flight. So if I draw the diagram here, this is your takeoff, then this is the climb, this is the cruise, this is the descent, this is the loiter, this is again descent, this is the landing. So these are the typical. Here is the takeoff, this is the climb, this is the cruise, this is the descent, this is the loiter. So these are some typical phases of the flight. As of now, we are here in this cruise flight. In this cruise flight, if you see, so this is the airplane. This is, if you see, this is the thrust. It is to be countered for the drag. There is a weight. There is a lift. So thrust is equal to drag. Lift is equal to weight. So this is the equation for steady state flight. Steady state flight. There is no acceleration in this type of flight. So we are discussing now in this type of things. We have also studied about the atmosphere. Atmosphere, then thrust required, thrust available, power required, power available, lift, drag polar. So CD is equal to CD naught plus KCL square. These all things we have already learned. And in fact here the CD is a function of CL. This we have already done, and we have done some numericals in the last few classes. I am just handling the numericals. So we will see that in this also we will see some numericals. I think we have the 5 numericals in this slide in this today's lecture. So let's go for the first one. A jet aircraft is initially flying steady and level at its maximum endurance condition. For the aircraft to fly steady and level but faster at the same altitude, so what we have to do? So a jet aircraft is initially flying steady state. So assume that this is your jet aircraft. So it is flying, this lift is equal to drag, this thrust is equal to drag, lift is equal to weight. So this is the steady state This is the state condition. So, for the maximum endurance condition, it is flying for the maximum endurance condition. For the aircraft to fly steady and level but faster at the same altitude, what pilot has to do? Okay, so there are increase the thrust, increase thrust and decrease the angle of attack, increase thrust and increase thrust and decrease. It is decrease, okay, not increase. Decrease angle of attack. Fourth one is reduce angle of attack. So just we will see which is the correct answer and why. So if this aircraft is flying, we have to maintain the same altitude. So if you increase the thrust, the velocity will be increased. So lift will be increased, so aircraft will start going upward. The first case, aircraft will start going upward. Second case, increase the thrust and increase the angle of attack. So in this, more upward it will be there. So velocity will be also increased, angle of attack, more lift. More than the first case. More than the first case, it will go upward. It cannot maintain. Because we want it should maintain also. Third one is increase thrust and decrease angle of attack. So you increase the thrust, so velocity will be increased, but if you decrease the angle of attack, then lift will be maintained. So this is the correct answer. Reduce the angle of attack, aircraft will start going down. So altitude will not be maintained. So answer for this problem is C, that is increase thrust and decrease angle of attack. So C is the correct answer. So here this you can see the C is the correct answer. Now we will see the next problem. This problem is also from GATE. So, an airplane requires a larger ground run to lift off on hot summer days because, okay, so if one aircraft is flying at a low temperature, some 20 degree, and another aircraft at a 50 degree or 45 degree hot summer days, so an airplane requires a larger ground run. So if it is more hot is there, so it needs more runway, more length of the runway. Why? So here T is directly proportional to density. So T is directly proportional to density, the first choice. So it is not, because it is inversely proportional. So this is not correct. T is directly proportional to the weight. T is directly proportional to the weight. Okay, so T is directly proportional to the weight. So this is correct answer, because as much you have the weight, you need more thrust. S, lift off is directly proportional to the density. This is also not correct. Runway friction, this is also not correct. So your B is the correct answer. So if you see here that T minus D by W, or T minus D is equal to W. So T is directly proportional to the weight of the aircraft. So T is directly proportional to the weight. So in this hot season, thrust will be reduced. Okay, so as per the case 1A, it is T is inversely proportional to rho. So it needs more runway to lift off the aircraft. Now, numerical number 3, highest limit of load factor experienced by civil aviation transport aircraft is in the range of. So we have to see what is the load factor. Load factor for civil aviation aircraft. This is the so here it is given 0 to 0.0 to 2. Next is 2 to 5, 5 to 8, 8 to 10. So this is for the general aviation aircraft. General aviation aircraft, UAVs and all. 2 to 5 is for, this is the correct answer, because for civil aviation we need load factor N is equal to L by W, that is 2 to 5. This is for the medium combat aircraft. This is the high performance fighter jets like modern F-35, 22, Rafale, J-22. This all will have in this range. Olden aircraft mix, Jaguars, Mirage and all, they will fall in this C category. But most of the civil aviation, Boeing, Airbus, Bombardier and all, they will fall in 2 to 5 category. So your answer number B is correct. Now I will go for the next problem, that is numerical number 4. An aircraft mass is 400,000 Newton, cruises at a speed of 240 meter per second at an altitude of 10 kilometers. Its lift to drag ratio is 15, assuming G as a 9.81 meter per second. Find the power in megawatt to cruise this plane. So we have to find out power in megawatt. So that we have to understand, that we have to convert units from watt to megawatt. So this we will see that mass of the aircraft is given 400,000 Newton. Speed is given 240 meter per second. Altitude is given 10 kilometer. Lift to drag ratio L by D is equal to 15. G is equal to 9.81 meter per second square. So we have to find the power in megawatt. So this is our story, and how to find out we will see in the next slide. Mass M is 400,000 Newton. Velocity is 240 meter per second. Height is equal to 10 kilometers. L by D is equal to 15. For steady and the level flight, we know that T is equal to drag, thrust is equal to drag, and this is equal to weight divided by D by L, or weight by L by D. So this is called the thrust required. Thrust required is equal to 400,000 by 15. You will get thrust required is 261,600 Newton. So this is this much Newton thrust is required. But we have to find out the power, and we know that power is equal to thrust into velocity. So thrust is 261,600 into 240. So here you will get that 62,789,000 watt. So divided by 10 to the power 6, you will get 62.789 kilo megawatt. So we have to find out the answer in megawatt. So power in megawatt is 62.789 megawatt. So this is the answer for this problem. And now I will go for my next lecture, which is numerical number 5. And this is a very interesting problem. We should try to solve this problem very systematically. I will read out this problem. A pitot probe on an aircraft is in a steady and level flight, reads a pressure of 55,000 Newton per meter square. The static pressure and the density are 45280 Newton per meter square and 0.6 kg per meter cube respectively. The wing area and lift coefficient are 16 meter square and 2 respectively. Find the wing loading of the airplane. So we have to find out W by S. So if you see here, the pressure is given at steady and the level flight is 55,000 Newton per meter square. Static pressure and the density. Static pressure is given 45280 Newton per meter square and the density is 0.6 kg per meter cube. The wing area and the lift coefficient, wing area is S is given and the CL is 2. So we have to find out how much loading of this aircraft is done. So here we will see that given is pressure is 55,000, static pressure is 45280, rho is equal to 0.6 kg per meter cube. We know that total pressure is equal to half rho v square plus ps and v is equal to 2 p naught minus ps by rho. 2 into p naught is equal to 55,000 minus 45,280 by 0.6. Velocity we will get here. By this equation we will get 180 meter per second. And we know that lift is equal to weight for steady state cruise flight, half rho v square SCL. So we have to find out W by S. So W by S is equal to half rho v square CL. CL is given, we have got this V here, rho is also given. So half 0.6 is a rho, this one. V is equal to this 180, CL is equal to 2. So if you put this value 1 by 2, 0.6 into 180 whole square into 2, you will get wing loading is equal to 19,440 Newton per meter square. Or you can also find out the weight because area is given. So the required weight of aircraft W is equal to 19440 into S. S is given 16. So into 16. So you will get this value here. I have not calculated. So this much weight of the aircraft is required for steady and the level flight. So this is our solution of problem number 5. Now we will see the next problem, problem number 6. Gross weight of the airplane is 7,000 Newton. It is capital Newton. Wing area is 16 meter square and maximum lift coefficient is 2. Assuming density at altitude is 1.23 kg per meter cube. Calculate stall speed. Calculate stall speed. So we have to find out the stall speed. Weight is given 7000 Newton. S is 16 meter square. CL is 2. Rho is equal to 1.23 kg per meter cube. So we can find out the stall speed by putting the equation. We know that L is equal to W is equal to half rho V square SCL. So if you want to find out the V, so the V square is equal to W 2W divided by rho SCL. V is equal to under root 2W rho by SCL. So W is given, rho is given, area is given, coefficient of lift is given, all the values are given. So we can write this velocity V stall under root 2 into 7000 divided by 1.23, area is equal to 16 meter square into CL is equal to 2. So at last you will get this V stall is equal to 18.859 meter per second. So this is the stall velocity which we are supposed to get by this equation. In the next lecture, I am going to discuss about this topic, climb and descent comparison, types of climb, different angles during climb, rate of climb, power available and the power required. The references for this lectures are Anderson J.D. Jr., Aircraft Performance and Design, International Edition, McGraw Hill's First Edition, Esley M.E., Aircraft Performance Theory and Practice, AIA Education Series. If any questions you are welcome to ask, you can write in the comment box in this video, or you can also send email to my yddwivedhi@gmail.com. Also, I request you people to like and subscribe this channel. Be tuned for my next lecture as per the given topic I am going to take very soon. Till then, thank you. Goodbye. See you again.
Like, share and subscribe. Hit the bell icon for more updates.